So hello and welcome to my presentation. My name is Johannes Popp and I'm a PhD student at the Technical University of Munich. The topic of my today's presentation is the numerical optimization of quantum cascade detector heterostructures. This was in collaborative work with our colleagues from the ETH Zurich. So start with a short outline. So a small motivation, some figures of merit for quantum cascade detectors, how we model our QCD scattering rates, and an introduction to our Bayesian optimization approach for QCDs. So what is a quantum cascade detector? A quantum cascade detector is a photovoltaic intersubband detector which reveals an asymmetric conduction band profile, as you can see also on the right side in the figure, which represents the conduction profile of such a device. And in the inset of the dashed blue box, or you can also see in the inset the wave functions of the ground level and the absorber level and the cascade. So we can extract photovoltaic current without applying any bias, so we have superior noise behavior. Due to the complex conduction profile, we have an increased design flexibility and we have the possibility to use the mature QCL processing techniques. Then what did we elaborate for our numerical optimization? So we elaborated a simulation approach based on scattering rates. Then we elaborated a Bayesian optimization approach applied to the QCD performance. We find an appropriate merit function for this and selected a suitable parameter space. So on the right side you can see a figure where we have in the blue box an inset of the 3 layers, and we could change the width of these layers a little bit and see what happened. Also another input parameter which we could change would be the doping density. So continue with the figures of merit. The one is the responsivity, which gives us the ratio of output current to input power. Here you can see in equation 1, this depends on the extraction efficiency, PE, and the absorption efficiency. And P is here the number of periods. But we are not only interested in the signal strength, but also in the signal to noise ratio, which can be measured by the specific detectivity. This is given in equation 2 for photovoltaic QCDs, where we have Johnson noise as the dominant noise source. Rp is here again the responsivity, and Rd is the detector resistance. So start with the extraction efficiency. The extraction efficiency specifies the probability that a photoexcited electron contributes to the photocurrent, and this is explained by the equation 3, where we have 2 parts. The right part gives us the net current to the adjacent periods, and the left part is the change in current from upper to lower laser level, where we have this induced absorption rate. Here on the right side you can see again the conduction band profile, and the arrows indicate here the possible scattering rates. One nice point here to say is, if we elaborate our model, which is not included here, the extraction efficiency only depends on non-optical rates, so we can cancel out this RP and have only consider here non-optical rates. Then to model the noise behavior, we introduce a resistance network. So our our levels became nodes, and the intersubstance transitions are included in conductance values as given in equation 4, which depend on the scattering rates and on the occupation. Here we assume thermodynamic equilibrium, and yes, so by solving the Kirchhoff's equation system, we can extract the total detector resistance. How do we model the scattering rates here? We use Fermi's golden rule to calculate the scattering rates for inelastic and elastic processes as given in equation 5. And which scattering mechanisms do we consider here? Optical phonons, acoustic phonons, interface roughness, alloy disorder, and impurity scattering. Now came to our Bayesian optimization tool for QCDs. So the aim of this work is to find the global optimum of our objective function. So we want to find input parameters for which we can optimize our merit function. The problem of this objective function is that it is a black box function. The evaluation can be or is expensive, so the simulation time and resources are high, and the outputs can be noisy. So the two main points of Bayesian optimization are: we have to define a Bayesian stochastic model for our objective function, so our surrogate model, and we have to select an acquisition function which gives us a good routine or a good way to choose the next sampling point. Yes. So let's focus on Gaussian process regression. A Gaussian process describes a generalized Gaussian distribution over functions. So we start with evaluating our objective function with some starting training input points. Therefore, we can then define the prior probability distribution, which is given in equation 7. We used here in Gaussian kernel, and by conditioning the joint Gaussian prior distribution on the observations, we can extract the posterior probability distribution, and from this the new function values f for input for test input points x asterisk can be sampled by this posterior probability distribution. Yes. Now to get an efficient and fast optimization result, we train the hyperparameters of the kernel function, and this is done by finding maximizing the marginal likelihood of the objective function for the training data or for our already evaluated points. So the next point is to choose an appropriate acquisition function. Here we have to think about exploitation, exploration. We have to think about both of these things. So exploitation means here the model believes that the mean function, the mean value is high at this input space values. And exploration means we also have to consider parts where we have higher uncertainty, so to speak. And a good choice here would be the expected improvement, which gives us strong theoretical guarantee and empirical effectiveness. So this is given in equation 10. T is here the target, and y is the function value. So and pyx is the marginal likelihood of our objective function at the input point x, input points x. Yeah, so we concentrate here on a well-known mid-infrared quantum cascade detector design, which is called N1022. This is detecting at 4.7 microns, And on the left side you can see the conduction band profile. Here the active transition will be in this well, and this is our cascade. We can extract rather good results. So blue is the experiment, orange is the simulation for higher temperatures. And then we start with the optimization by changing the 3 adjacent layers, 2 barriers in one well, to the active well. Yes. So we use here a space-filling Hilbert curve to visualize our optimization problem from a multi-dimensional input space. So the Hilbert curve maps an n-dimensional curve to R, and this is implemented in the Aftershock project, which is a project by our colleagues from the ETH. So here are the results presented in the abstract. We can find we have varied these 3 aforementioned layers in 0.5 angstrom steps at a temperature of 220 Kelvin, where we have a good match to the experimental results. We use the 3rd order space filling Hilbert curve with 512 input points. The nominal structure shows a detectivity of around 1 × 10 to the power of 8 joules. We trained our model with 42 simulation evaluations, and we can improve the detectivity by a factor of around 2.6. So there you should also include 10 to the power of 8. And as you can see, the experiment's a little bit volatile, so we decreased our step size to 0.1 angstrom and used the 3-dimensional input space without using the Hilbert curve. And we did 4 simulation evaluations in parallel and ended after 4.5 simulation evaluations. And as you can see, after 9 evaluations, we have reached the optimum. So last but not least, a small conclusion. The numerical optimization of quantum cascade detector structures was presented. We presented a compact and robust approach for the determination of the specific detectivity. We calculated this inter-subband scattering rates by Fermi's golden rule. We used a sensitive and precise Bayesian optimization algorithm to improve for our nominal structure the detectivity by a factor of 2.6. So, and a small outlook. So we will repeat the simulation of the last slide to validate our convergence, and we will run multiple Bayesian optimization runs. Then we want to include our Ensemble Monte Carlo approach, which is a self-consistent approach to calculate to simulate the inter-subband scattering rates, and hopefully the optimized design or optimized low noise detector can then be used in a QCL-based dual-comb spectroscopy system. So thank you for your attention,